Hello all. Today we discuss about 8085 interrupt process. The 8085 interrupt process is controlled by the interrupt enable flip-flop, which is also known as interrupt enable flip-flop IE, which is internal to the processor and can be set or reset using software instruction. If the flip-flop is enabled and the input to the interrupt signal INTR goes high, the microprocessor is interrupted. This is maskable interrupt, that is, it can be enabled or disabled. The 8085 has non-maskable and 3 additional vector interrupt signal as well. And first of all, there are 2 instructions are available for enable or disable the interrupt. So first of all, we discuss about enable interrupt. This is the enable interrupt instruction. This is 1 byte instruction, and this instruction sets the interrupt enable flip-flop and enables the interrupt process, and system reset or an interrupt disable the interrupt process. Next instruction is known as DI, which is also known as disable interrupt. This is disable interrupt, and this instruction is used to disable the interrupt process. This is 1 byte instruction, and it should be included in a program segment where an interrupt from an outside source cannot be tolerated. So in a 8085, basically, first of all, if we consider this is an 8085, so there are 2 pins associated with it. One is INTR, that is called interrupt request, and another is called interrupt acknowledgement. This bubble signify this is an active low. This bubble signifies this is an active low signal, and if this INTR pin goes high, then the interrupt process is start, and the microprocessor either interrupted or not. This is signified by the low signal at the interrupt acknowledgement signal. Okay, by this interrupt acknowledgement signal. So first of all, we discuss about there are basically 2 different types of interrupt. One is software interrupt and another 2 is hardware interrupt. In the hardware interrupt, in the later video we will discuss about that. So first of all, in this lecture we discuss about what are the software interrupt. Basically, these INTR and INTA process are called as a software interrupt because using this INTR there are 8 restart instructions are generated. Now let us talk about that. The 8085 instruction set included 8 restart instruction. Okay, so if we look in the 8085 instruction, so there is 8 restart instruction, also known as RST instructions, are available, which is from RST 0 to RST 7. Okay, these 8 instructions are supported, and there are 1 byte call instruction that transfer the program execution to a specific location on page 00. Page 00 means starting from location 0000 hexmode location, that is page 0. In a page 0 means the starting location is 000 hexadecimal memory location. Okay, the RST instruction are executed similar way to the call instruction, and the address in the program counter, meaning the address of the next instruction to an RST instruction, is stored on the stack before the program execution is transferred to the RST call location. Okay, when the processor encounters a return instruction in the subroutine associated with the RST instruction, then the program returns to the address that was stored on the stack. Okay, but in case of hardware interrupt, we'll use an RST instruction to restart the program execution. Okay, so first of all, the interrupt process. So how to interrupt process start? So when this pin goes to high, this pin goes to high, then interrupt request signal, interrupt acknowledgement signal goes to 0, and using this interrupt acknowledgement signal we can activate generally 8 different restart instruction. Okay, so basically if we discuss the RST instruction, so first of all, this is an mnemonics. This is called the mnemonics. The mnemonics are from RST 0, RST 1, RST 2, RST 3, RST 4, RST 5, RST 6 and RST 7. Okay, and these are the hex code for different restart instruction, and this is the call location. There is one formula to determine the call location. So first of all, this is the hex code is C7CF, then next D7DF, then E7EF, and last one F7AFF. Okay, and what are the call location? The general rule is that if it's the typical from is RSTN, then we multiply this n with 8 because there are 8 instructions. So then this is expressed in a decimal, and then we convert in a hexadecimal form, and this hexadecimal form is the call location or the memory location. So first RST 0, so here n equal to 0, that means 8 into 0 0, so therefore in a 4 digit hexadecimal display look like that. 8 into 1, that means 8. So what is the hexadecimal code of 8? 0008. Next 8 into 2, 16. So 16 is a hexadecimal decimal form. So what is a binary? 10. So basically 0010. Next one is 3 into 8, 24. That means 0018. Next one is 4 into 8, 32. That means 0020. Next 0028, and similarly 0030 and 0038. Okay, so these are the call location, that and also known as the memory location. And using INTA bar signal sent out instead of a read bar signal. Okay, so now we discuss about our hardware section of the circuit implementation of the RST instruction. So here we connect one tri-state buffer. This is a tri-state buffer. So there are 8 internal tri-state buffer are connected. Okay, to this is 3, number 3, this is 4, this is 5, this is 6, this is 7, and this is 8. Okay, and now if we connect, this is logic 1, and this is connected to ground, and these all 4 bit are logic 1 connected to logic 1. So now this is one resistance is connected here, which value is 10k, and this is connected to plus BC, that means plus 5 volt, and this is generally ground. So what is the output? And there is one chip select pin is available, and from this chip select pin is connected to INTA bar. This INTA bar coming from 8085. So when INTA goes to low, then this tri-state buffer will be on, activate, because for a tri-state buffer, the third control input of this tri-state buffer, okay, are connected to this chip select. So when this pin goes to low, that means chip select tri-state buffer is selected, and then the input is present at the output. So what is output? 1 1 1 0 1 1 1 1. So now this is the 7-bit position, and this is a 0th-bit position. So what is the status? Status is 1 1 1 0 1 1 1 1. So what is hex code? The hex code is EF, and this EF is the hex code of RST5 instruction. So what is RST5 location? 5 into 8, 40. That means 0028. So this is our memory page, where after interrupt process the call location is 0028. Okay, so now we discuss about, this is an hardware setup, how interrupt process, how by using INTA signal the interrupt process is started, and also associated with the INTA bar signal. Okay, and the restart instruction is placed on the data bus during the machine cycle M1. Okay, first of all, it is noted that the RST instruction is placed on the data bus during M1, because when INTR is pressed and INTA gets low, then from this hardware the RST5 instruction is placed on the data bus during machine cycle M1, and during M1 the program counter holds the memory address of the next instruction, which should be stored on the stack so that the program can continue after the service routine. And during the machine cycle 2, the address of the stack pointer -1, but that means SP-1 location, is placed on the address bus, and the higher address of the program counter is stored on the stack. And during M3, the lower address of the program counter is stored on the next location sp-1, sp-2, sorry. That means if we consider from the starting location, that means if we consider that our program is starting from here, okay, this is the main program, and now anywhere we place the INTR signal. So here INTR is placed, that means the microprocessor is interrupted, and then INTA goes low, and if INTA goes low, then this restart instruction is placed on the data bus. But where the INTR is placed, say when microprocessor execute 8002 location, then interrupt gets low. Now this 8003 is say the stack location, that means if stack pointer is located at FFFF, okay, then at FFFE it stored first, what is the value? It stores the first higher order address, that means 80, and then FFFD it will be stored the address 03. So this is storing the stack, because after returning from the interrupt process or interrupt service routine, we will continue in the main program. So that's why microprocessor will saved in this 8003 program counter location in the stack memory location, and when interrupt process is done, then it again it's come back to the main program. So this is done in the M2 cycle, and this is done in the M3 cycle, okay, or machine cycle 3, and in the machine cycle 1 the restart instruction is placed on the data bus, okay. This is very important. And there is a 3 status pin, just to talk about that. We also know that there are 3 status pin, IO/M1, and number 2 is S0, and number 3 is S1. These 3 are becoming 111 because this is an interrupt process, okay. So just summary on that, during M1 machine cycle the RST5 is decoded. It is a 1 byte call instruction of location 0028, and the machine cycle M2 and M3 are the memory write machine cycle that stored the content of the program counter on the stack, and then a new instruction cycle is begin. Now in the next instruction cycle the program counter is transferred to, now when our main sequence is starting from the 8000. So when it is occurred, then it jumps to the 0028 because this is an RST5 location. Now see the sequence. This is how the interrupt occurs in the 8085. Now when it jump, program counter is jumped to 0028 location, the service routine is written somewhere else in the memory. So now in this location there is one jump instruction is say jump 9000. So now this is the target location, and this is specified by the development board, which is made by the various type of developer, like a Dynalog or ALS kit, different types of UP85 model. There are lots of kit are available in the market, and they are mentioned their own specific programming location for and now we consider the program location is, and 0028 there is a jump instruction is written, and what is the location? This is 900, and now in this 900 here our interrupt service program is written, and this is also known as interrupt service routine, okay. And the service routine is written somewhere else in the memory, we talk about that, and the jump instruction is written at 0028. Students, please note that in 0028 there is no ISR is written, okay. There is no ISR in the 0028 because it is very confusing concept. But to clear to understand that in a 0028 there is a jump instruction is written. Jump, what is address? This address is specified by the different manufacturer, and now you starting from this address, our program, this program is also known as interrupt service routine, okay, clear. And after interrupt service routine is occurred, then it's returned back to the main program, and then main program operation is completed, okay. So one thing should be remembered, that our 8085 timing of the interrupt acknowledgement machine cycle and the execution of RST instruction is more important, okay, because using this machine cycle of the RST instruction we get the clear knowledge. We get the clear knowledge, okay, clear knowledge of the interrupt acknowledgement process. So please note that in a M1 machine cycle the RST5 instruction is decoded, and in this machine cycle the RST5 is decoded from the external hardware circuitry as shown in the previous slide, In the machine cycle M2, what is the machine cycle M2? In the machine cycle M2, the higher order address is stored in the stack, and in the M3 machine cycle, the lower order memory address of the main program, or the lower order address or the next instruction of the main program is stored. Okay, lower order address. So this is M2 in the higher, this is M3 is the lower, and this M1 cycle requires 6 T states. This is required 3 T states, and this required 3 T states. So therefore 12 T states are required to execute the any instruction for interrupt process. Okay, so this is the process by which the instruction is interrupt process is. So this is basically known as the software interrupt, because if we changes the RST5, RST6 and RST7, then the call location is also changes. So that's why it is also known as the software interrupt purpose, used also in the software interrupt concept. Okay, so this is the basic concept of software interrupt. So now we discuss about our another interrupt process known as, this is very much important, it is also known as hardware interrupt or 8085 vector interrupt. Why this is known as vector interrupt? Because their call location are fixed, they are not changing. For any developer, like a Dynalog, like a UP85, like any Intel or Philips, any developer which developed the microprocessor development board, these call location are not changes, because okay, this is fixed. The 8085 has 5 interrupt input. One is called int interrupt, which is discussed earlier in the slide, and there is 3 signal also known as RST 5.5, 6.5, 7.5 respectively, and the 5th is called the trap. So there is another interrupt pin are available, RST 5.5, RST 6.5, RST 7.5, and this is called trap. Okay, for these 4 interrupt pin, these 3 interrupt is called maskable, because it can be disabled or enabled by using software instruction, but trap is not a disable process until the microprocessor is resetted. Okay, and the last 4 RST and the trap instruction are automatically vectored or transferred to the specific location on memory page 00 without any external hardware requirement. They do not require any INT bar signals or an input port, and the necessary hardware always implemented inside the 8085. Okay, this interrupt call locations is like this is a trap first of, and then RST 7.5, and then RST 6.5, and then RST 5.5. This trap is location is 0024. This is the location of 003C. This is the location of 0034, and this is the location of 002C. Okay, the trap has highest priority, followed by RST 7.5, 6.5, 5.5 and INTR. So between these, first of all, the highest priority is trap. That means if all interrupt is activated in the same time, then trap is first executed, then 7.5, then 6.5, then 5.5, and then last is INTR. INTR is the lowest priority. Okay, this is very important. And however, the trap has a lowest priority than the hold signal used when you use the direct memory access concept. In the later video we discuss about the direct memory access. Now trap is a non-maskable interrupt known as NMI. This trap is also known as NMI, that means non-maskable interrupt. That means it cannot be disabled any software instruction, and next one, it cannot be disabled, and next one, it is level and age sensitive. That means the input should be goes high and stay high to be acknowledged. It cannot be acknowledged again until it make a transition from high to low to high. And next one, 3 maskable interrupts are RST 7.5, 6.5, 5.5. These interrupts are enabled under the program using the instruction element interrupt or set mask interrupt, and also the status is read by the read interrupt mask or REM instruction. Okay, so this is the general concept of software interrupt and hardware interrupt in 8085. So now we discuss about what is the 8085 interrupt and the vector location and the internal hardware diagram of this interrupt process. Okay, now this is an 8085 interrupt and vector location internal hardware diagram. So first of all, this is an RST 7.5. so this is an H triggered. So this is an D flip flop when this is activated, and then the D is 1, and then there is AND gate equal to 1, and these three bits, this is 1 2 3, these bits are mask bits. These bits are connected to the accumulator bit when SIM instruction is executed, and these are the output memory address location. This is for RST 7.5, this is for 6.5, and this is for RST for 5.5, and this is for trap. Here look, that trap is directly, there is a no AND gate connection between the trap signal and the memory selection, because when trap is activated, is directly selected to the 0024 memory address, and using these 3 bit we can mask the bit of the RST 7.5 to RST 5.5, RST 6.5 and RST 5.5. 3 interrupt are enabled using this marks bit. And one thing should be remembered, any interrupt process is starting, the enable interrupt should be necessary, because when enable interrupt is 1 and this equal to 0, then these output equal to 1, and then 3 AND gate equal to input equal to 1. Because if enable interrupt is not done, and if disable interrupt, this pin is a disable interrupt pin, and if disable interrupt pin is get high, then these output equal to 0. So therefore no interrupt, that means RST 7.5, 6.5 and trap are not activated, and similarly also INTR also, because these output is connected to this AND gate. Okay, so only one interrupt trap which is not maskable, not maskable interrupt. That's why it is called NMI, non-maskable interrupt, and it cannot determine also the enable interrupt. Okay, so this is very important. Now this is INTR. When INTR gets activated, this AND gate, when enable interrupt is process is 1, then these 1 is get selected, and then there is a 8 different RST instruction is supported. This is for RST 0, this is RST 1, this is 000, this is 0008, this is 0010, this is 0018, this is 0020. For different memory location, this is for RST instruction, this is for software interrupt purpose, and this is for hardware interrupt purpose. And one thing should be remembered, when this reset pin is activated, then there is an RST 7.5 is also disabled, and this pin is also known as RST 7.5 interrupt recognized. And there is 2 pin are available. This also pin, the reset, this reset and the upper reset are 2 are the common signal, and this is known as any interrupt recognized signal pin. So this is the internal hardware, how interrupts are occurred for, and how it is maskable and non-maskable using the SIM instruction, and their bits, 3 maskable bits are shown here. And now we discuss about our SIM instruction is very important, because using this SIM instruction, this is a format of the accumulator when SIM instruction is executed. So first of all, this is serial output data, this is serial enable. These 2 are not associated with interrupt. This is for the serial communication. This bit is a don't care bit, and now this is R7.5, that means this bit is known as reset 7.5, and RST 7.5 flop is reset off using this bit. This is known as mark set enable. One thing should be remembered, when this bit equal to 0, then the 3 bits, that means 0 1 2, this is 3, this is 4, this is 5, this is 6, this is 7. So when this bit gets low, then these 3 bits are ignored, and if this 1, then 3 bit are known as marks is set. So now the individual pin function is, this is called mark 7.5, this is called mark 6.5, this is called marks 5.5, and these 3 bit 1 2 3 bits are basically these 3 bits here. This is this 3 bit, so this is known as M7.5, this is known as M6.5, and this is known as M5.5. This is M5.5. Okay, so now when this is pin gets low, then this is masked, and if 0, then this is available. So when 1, the interrupt is masked, and if 0, the interrupt is available. Similarly for 0 for available, 1 for masked. This is also 0 for available, 1 for masked. So this is the SIM. instruction pattern of accumulator. SIM instruction is basically the interpretation of the accumulator bit pattern for the SIM instruction. So when SIM instruction is executed, the accumulator bit pattern is look like that. Okay, and SIM is a 1-byte instruction and can be used for 3 different functions. One function is set to set the mask of RST 7.5, 5.5 and 6.5 and 5.5 instruction. Okay, so using this instruction we can disable or enable the interrupt flip-flops. Second function is the reset RST 7.5 flip-flop. So this default bit. So first of all, using these 3 bit we can disable and enable the RST 7.5, 6.5, 5.5 individually, and using this bit we can reset the RST 7.5 flip-flop. Okay, and this is an additional control for RST 7.5. If default is 1, then RST 7.5 is reset. And the third function is to implement the IO, simple input output. That means we already know that the 8085 is transfer the data parallel using the parallel bus D0 to D7. So using these 2 pins, we transmit the serial data from the microprocessor to the peripheral device and vice versa. Okay, so they are the 3 functions of is very important for SIM instruction. Okay, so now we talk about the next instruction, which is known as RIM instruction. So this is the format of RIM. What is the meaning of RIM? Read interrupt marks. So this is basically for the monitoring purpose, and now we interpret the accumulator bit pattern for the RIM instruction. So first of all, this is used for serial input data. This is for one function. This is I7.5. I means there is a pending interrupt, I6.5 and I5.5. This is basically the monitoring purposes. Interrupt enable, this is called the pending interrupt 1 for pending. If this bit gets 1, then the interrupt is pending. This is interrupt enable. Okay, this is interrupt enable. If 1, this is enabled, and the 3 bit is M7.5, M6.5, sorry, and M5.5 also here. This is interrupt mask. If 1, these bits are masked. So this is for the not a set purpose, this is for the read purposes. And instruction RIM checks for a pending interrupt. Okay, so this is the RIM instruction. Load the accumulator with the different types of information as far as the user specify or different types of application oriented. And this is a 1-byte instruction, and the 3 function is of the RIM is to read interrupt marks, and these instruction load the accumulator with 8 bit indicating the current status of the interrupt mask. And second one is to identify the pending interrupt bit D4 D5, that is this is 0 bit, this is 1, this is 2, sorry, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So bit D4 D5 D6, that means 4 5 6, these 3 bits are identify the pending interrupts, and to receive the serial data bits G7 is used. Okay, and these 3 bits are basically used for to read the interrupt mask and loads the accumulator with 8 bit indicating the current status of the okay. So these information are coming from the interrupt status and load in the 8085. Okay, so that's why it is called the read interrupt mask, to sense this pending interrupt status. Okay.